So I'll be talking about QMA versus QCMA and pseudorandomness. And this is joint work with Jiahui Liu and Henry Yuen. Um, so the main result that I'll be focusing on is following. Distinguishing between whether an exponentially large graph, given oracle access to it, has two disconnected components or has a single expanding component. This task separates QMA from QCMA, assuming a certain quantum pseudorandomness conjecture holds. And this is evidence that quantum proofs can convince verifiers of more complex statements than classical proofs. And the quantum pseudorandomness conjecture is interesting in its own right because it's connected to open questions about quantum speedups for solving unstructured problems. And it's also connected to something called the Aronson-Ambinus conjecture, which is about influences of low-degree bounded polynomials. So I'll start by talking about some quantum generalizations of NP. I'll start with quantum Merlin-Arthur, which is QMA. And informally, QMA is problems that are efficiently verifiable on quantum computers with the help of a quantum proof. And formally, we say that a language is in QMA if and only if there exists a polytime quantum verifier V such that if X is in the language, then there exists some quantum proof psi where V X comma psi accepts with high probability. And if X is not in the language, then there does not exist any quantum proof psi that will cause the verifier to accept this instance X with high probability. And pictorially, we have Merlin, who's all-powerful but untrusted prover, and we have Arthur, who's an efficient verifier, quantum verifier, and they both get some instance X, and then Merlin sends over a quantum proof psi, and the task is for Arthur to accept or reject. Okay, and some well-known problems in QMA is the local Hamiltonian problem, which is the problem of deciding if there exists a quantum state with energy at most alpha or at least beta, where it's promised that alpha minus beta is at least 1/poly. And this problem is QMA complete. And a problem that's co-QMA complete is the circuit equivalence problem, which is the task of deciding whether two quantum circuits are equivalent, or rather not equivalent. And okay, so going on to quantum classical Merlin-Arthur, or QCMA, and informally, QCMA is a set of problems that are efficiently verifiable on quantum computers with the help of a classical proof. And formally, a language is in QCMA if and only if there exists a polytime quantum verifier V such that if X is in the language, then there exists a classical proof W where V X comma W it accepts with high probability. And if X is not in the language, then all classical proofs W cause the verifier when it's given as input W to reject with high probability. And some problems in QCMA is the ground space connectivity problem. And this problem is the setup is the following. So we're given a local Hamiltonian, and we're given polynomial size descriptions of two ground states, and we're promised that such descriptions exist. And the task is to decide if there exists an energy barrier between these two states. And this problem is QCMA complete. So the task is to decide if there is a series of 2-qubit gates that you can apply from one state to get to the other state while keeping the energy low. And now I'm going to talk about oracle separations of QMA from QCMA. So before doing that, I'll have to define what oracle QMA and oracle QCMA are. So these are just oracle models of QMA and QCMA. And these models, the input to the verifier, and prover, instead of it being some instance X that's in the language or not in the language, the input is an oracle, and the verifier queries this oracle. And the complexity parameters, they're measured in terms of two things: the number of queries made by the verifier to this oracle, and the size of the proof received by the verifier, or the number of qubits in the state psi received by the verifier. And the verifier is allowed to make queries to this oracle, and its task is to decide whether the oracle satisfies some property. So that's oracle, QMA, and QCMA. And now a QCMA, QMA oracle separation, it's a decision problem, L yes, L no, where L yes and L no, they're sets of oracles. And it's a decision problem where one, there exists a QMA verifier V that can decide this problem using polylog capital N queries and proof size. And any QCMA verifier needs at least poly N queries or poly N proof size. And N here is the size of the oracle, or it's the size of the truth table of the oracle. And such a separation, so a separation would involve coming up with such a decision problem that satisfies 1 and 2. And such a separation, it provides a setting where quantum proofs are more powerful than classical proofs. So what's known in this regime? It's known that there is a unitary oracle. By unitary, there's a quantum oracle separating QMA from QCMA. And the oracle decision problem in this setting is the following. The task is to decide, so both the prover and the verifier, they get access to some unitary, and the task is to decide if this unitary acts as is the identity, or if it's a reflection for some state psi. And we're promised that the unitary that they're querying, it's one of these two cases, and the task is to decide which case it is. And the QMA upper bound is easy. The prover can just send over the state psi, and the verifier can prepare a query to the oracle, to this unitary oracle, to check if U adds a minus sign on the state psi. So and the QCMA lower bound, intuitively, the high-level idea is the following. So here is the state size, a uniformly random state. So intuitively, the QCMA verifier, without making exponentially many queries, it cannot distinguish these two cases of unitaries because psi is a uniformly random. It's a Haar random state. Okay. And a question that was left open in this separation by Aronson and Kuperberg was if there's a classical oracle separation between QMA and QCMA. And what do I mean by classical oracle? A classical oracle is just a function, f, classical function, which is queryable in superposition. And there's been partial progress in this question over the years. All of these results, they either assume some type of restriction on the oracle model or on the verifier. And the first few separations, they're based on graph problems. So the sets of oracles, they're sets of graphs that are satisfying some property or not. And Mutreja and Yuen, for example, they showed that a randomized oracle variant of the problem separates QMA from QCMA. So this assumes a restriction to back up a bit. In 2011, Lutomirsky, he proposed the components problem as a candidate QMA-QCMA oracle separation. And Mutreja and Yuen made progress towards showing that this problem acts as a QMA-QCMA oracle separation by showing that an oracle variant of this problem separates QMA from QCMA. And we show the same for assuming no restrictions on the oracle, but assuming a quantum pseudorandomness conjecture instead. So before I get into the separation, we'll have to define what a graph oracle is. So graph oracle, it takes in a variable r, which I'll call color, and it takes a vertex n and it outputs some other vertex. And this function, it's a graph oracle if it defines a matching for every color r in big R. So meaning f of r comma x is y and f of r comma y is x. So you can think of this function as a union of matchings because every color r defines a matching. So yeah. And the components problem is the following. It's the following distinguishing task. And you're given a graph oracle where the yes instance, the graph oracle is a yes instance if the corresponding graph that arises from this function f, it can be partitioned into two components of equal size, so of size n over 2. And it's a no instance if the graph arising from this function f is a delta expander. And so in particular, no instances, not only are they not partitioned, but they're a single component that is very highly connected. And so starting with the QMA protocol for components, to recall that for yes graph oracles, there is a balanced partition and no edges across the partition. So the intended quantum proof is just the state psi, which is a uniform superposition over the vertices in the graph, but there's a minus sign attached to all the vertices that are in the second component. It doesn't matter which is the second component in this case, but yeah, so it's a uniform superposition with a minus sign attached to all the vertices that are in the second component, so you can think of it as bar. And this state is specified by log big N qubits, and log big N will say it's little n. And so some intuition for why this proof is able to convince the verifier. The verifier can be convinced using this proof by performing one of two tests at random. The first test is the balancedness test, and this test checks that the state psi that the prover sent over is orthogonal to the uniform superposition over all vertices without any minus signs, so just the uniform superposition over all vertices. And the second test is the expansion test. So in this test, the verifier picks a random color little r, and it checks that psi, the state psi, is invariant under permuting the vertices according to the matching that's described by this color that the verifier picked. So intuitively, the first test, it checks that psi indeed is a balanced partition of vertices. And if it is a balanced partition, then it's easy to verify that the state psi will be orthogonal to the uniform superposition. So if the size of the first component equals the second component, then the first test, the psi will pass. And the second test, intuitively, it's checking that not too many edges cross the cut specified by the state psi. So again, the second test intuitively it's checking that the state is invariant under permuting the vertices according to the matching for this random color that's picked. And so that's the intuition for the upper bound. And now the QCMA lower bound for this components problem, the main theorem is the following. So assuming a certain quantum pseudorandomness conjecture holds, any QCMA protocol for components, it must either make n to the theta 1 queries to the graph oracle f, or it must receive a classical witness of length n to the theta 1. And just to highlight the separation here, the QMA verifier only had to make one query, and it received a witness that was little n qubits long. So this is a big separation. So before I get into the separation, I'll start by talking about the quantum pseudorandomness conjectures that we assume. So I'll start by defining a dense distribution. So we say a random variable x over 0, 1 to the n, it's delta dense if for all subsets S of coordinates, the min entropy of the random variable restricted to the subset S, it's at least 1 minus delta times the size of S. So what this means is that you can look in any window of these coordinates, and you have the guarantee that the min entropy of this random variable restricted to that window, it's at least 1 minus delta times the size of the window. And for example, if we consider X to be the uniform distribution over all even parity strings in 0, 1 to the n, then this distribution is 1 over n dense. And so now that I defined what a dense distribution is, the warm-ups, I'll start by describing a warm-up version of the pseudorandomness conjecture we use. And it says the following: for all T-query quantum algorithms A, for all delta dense distributions F over 0, 1 to the n, probability over F that A to the F outputs 1 minus the probability over U that A to the U outputs 1. It's upper bounded by poly T, poly delta. And U here is the uniform distribution over 0, 1 to the n. That's the warm-up pseudorandomness conjecture. And this conjecture is motivated by results in classical cryptography, which show that dense distributions fool few query classical algorithms. So in other words, in the classical setting, this conjecture it's known to be true. So for all T-query classical randomized algorithms A, and for all delta dense distributions F over 0, 1 to the n, it's true that probability over F that A to the F outputs 1 minus the probability over U that A to the U outputs 1 is at most, the absolute value of this quantity is upper bounded by delta T. And this results in cryptography, it's used to argue that short advice about a random oracle cannot be helpful. And the warm-up pseudorandomness conjecture that I talked about, it was shown in 2021 that it implies a long-standing conjecture called which I'm calling the no quantum speedup conjecture from the late 90s. And what is the no quantum speedup conjecture? It says that for all T-query quantum algorithms A, there exists a classical algorithm B making poly T, 1 over epsilon queries such that probability over U that A to the U outputs 1 minus the probability over U that B to the U outputs 1 is upper bounded by epsilon. And here U is the uniform distribution over bit strings. And so intuitively, this conjecture is saying that there cannot be an exponential quantum speedup for unstructured decision problems, which is why we, because it's about uniform distributions. So the warm-up pseudorandomness conjecture, it implies this well-known conjecture that I call the no quantum speedup conjecture. And furthermore, the no quantum speedup conjecture, it's also implied by something called the Aronson-Abinas conjecture, which is about influences of low-degree polynomials. And the Aronson-Abinas conjecture says that all degree T polynomials, P, they have a highly influential coordinate. So they have a coordinate J where the influence of J is at least poly variance of P over T. And this conjecture is still open, but there's been some partial progress in proving variance of this conjecture, restricted versions of this conjecture. But this conjecture is still open. So just to zoom out a bit, so we talked about the warm-up pseudorandomness conjecture, which says that dense distributions fool quantum algorithms. Talked about the Ernst-Magnus conjecture, which says that low-degree bounded polynomials, they have a highly influential variable. And then we talked about the no quantum speed of conjecture, which says that quantum algorithms can be simulated by classical algorithms on the uniform distribution. So how are these all connected? Both the warm-up pseudorandomness conjecture and the AA conjecture, both of these imply the no quantum speed of conjecture. And if I talk about the warm-up pseudorandomness conjecture in terms of polynomials, so if I assume that dense distributions fool low-degree bounded polynomials, then this statement would imply both the warm-up pseudorandomness conjecture and the AA conjecture. And in fact, it would imply all these conjectures. So that's how the warm-up pseudorandomness conjecture and the AA conjecture are connected, is through this polynomial version of the conjecture. So that's all the conjectures. And now, so just to build some confidence that this on this conjecture, we can prove that a weaker version of this warm-up pseudorandomness conjecture, it is true. So what do I mean by weaker? We can prove the following statement. So it's for all degree t polynomials, for all delta dense distributions f over 0 1 to the n, and for all epsilon bigger than 0, the expectation over the polynomial on f minus the expectation of the polynomial evaluated on u, it's upper bounded by this quantity. And the thing to take away from this bound is that the dependence on t is exponential. So, so in particular, if t is logarithmic in big N, then this is a good bound, and this is proven using the Fourier tail bound from prior work. And if we can get this dependence on t to be polynomial, then that would be great, and that would prove the conjecture. So this conjecture here, it's not completely outlandish. There's here's some evidence to support it. And now, so I call this conjecture the warm-up pseudorandomness conjecture because the conjecture that we end up using in our QCMA lower bound, it's about permutations. And so in particular, we consider algorithms that query permutations and their inverses. So it's just a slight change in the model, but the statement is more or less the same. So similarly to the function case, I can define a delta dense permutation, and we say that a random permutation P over N is delta dense if for all subsets S of coordinates, the main entropy of the main entropy of this permutation, the margin restricted to S, it's at least 1 minus delta times this value, and the summation is this quantity is just the main entropy of a uniformly random permutation on S. So the quantum pseudorandomness conjecture that we use, it's the following. It says that for all t-query quantum algorithms A, and for all delta dense random permutations P, from n bits to n bits, probability over P that a to the P outputs 1 minus probability over U that a to the U outputs 1, it's upper bounded by poly T, poly delta. And U again it's a uniformly random permutation over N. And if you replace t-query quantum algorithm with a classical randomized algorithm, then this is known to be true, and it was proven in prior work. And this again has applications to cryptography. So now that I've described the quantum pseudorandomness conjecture, now assuming this conjecture we can conditionally separate QMA from QCMA. So recall that I already showed the QMA upper bound, and now we'll talk about the QCMA lower bound. So the main theorem is, to recall, assuming the quantum pseudorandomness conjecture, any QCMA protocol for the components problem must either make n to the theta 1 queries to the graph oracle F, or it must receive, n to the omega 1 queries to the graph oracle F, or it must receive a classical witness of length n to the omega 1. And this is a win-win situation, because either the quantum pseudorandomness conjecture is true, and there is a classical oracle separation between QMA and QCMA, or the conjecture is false, and that implies that there's quantum advantage in distinguishing dense permutations from uniform permutations. So either one of these scenarios would be very interesting. So we'll start by assuming that there is some QCMA verifier V that solved the components problem with n to the little of 1 queries and n to the little of 1 proof length. So this means that for every, so now we'll look at the yes instances of graphs. So if we assume that there is a QCMA verifier that solved the components problem, then for every yes witness is associated with some, every yes instance, it's associated with some witness W, such that when the verifier queries this yes instance and it receives W as a witness, it will accept with high probability. So now for every witness W, we can define the set F sub W, which is the set of all yes instances, F, such that V to the F, when it's given as input witness W, it accepts with high probability. So now this implies that there exists some maximizing witness W star, such that the number of yes instances that this witness makes the verifier accept is the maximum. So you can think of this blue region as the set of all yes graphs. So it's F sub yes. And every yes graph has some witness W that makes the verifier accept. And W star is the witness that is maximizing, in the sense that it has the most number of yes instances associated with it. So the first step in the proof, assuming that we have this QCMA verifier, the first step would be to hardwire this maximizing witness W star into the verifier to now remove the witness, and to get a T-query algorithm V star, which is hardwired with W star, that accepts all yes instances in F sub W star with probability at least, say, 9/10. And it rejects all no instances with high probability. So now we've transitioned, we removed the witness, and we're talking about just a query problem now. So we have the guarantee that we have some, we have some algorithm V star that makes n to the little of 1 queries to graphs in to the graph oracle, and it accepts yes instances F and F sub W star with probability at least 9/10, and rejects all no instances. And now the goal is for me to invoke the quantum pseudorandomness conjecture somehow. So now I'm going to bring in these permutations and try to invoke this conjecture somehow. So how do we do that? The first step is to observe that we can view yes graphs in the components problem as functions of raw permutations, 2R plus 1 raw permutations, where R is the number of colors. And what do I mean by that? So the X permutation, we can think of it as specifying a partition of vertices into 2 components. So the first component specifies the vertices that'll be in component. The top half of this permutation, it specifies vertices in the first component, and the bottom half of this X permutation, it will tell us which vertices are in the second component, or S bar. And once we've described this partition of vertices, now Y sub R is a permutation over each component. So it's a permutation over n over 2 vertices because each component is of size n over 2. And now Y sub R, within each component, it's going to, Y sub R, within the first component, it's going to specify the rth matching. So the X permutation partitions these vertices into two components, and the Y sub R permutation, it specifies the rth matching in the first component. And similarly, the Z sub R permutation, it specifies the rth matching in the second component. So this is why we need two R plus 1 permutations. We need one permutation to specify the partition of the vertices in the two components. And then we need one permutation for each color in each component that specifies the matching within that component. And Y sub R specifies the rth matching in the first component, and Z sub R specifies the rth matching in the second component. So therefore, we can view every yes graph as some sequence of raw permutations, X, Y1 through YR, and Z, Z1 through ZR. And now we can think of this. So there's an algorithm V star that makes queries to some graph oracle F. And now we can imagine that this graph oracle F itself, it's making queries to these permutations. And because R is a constant, we can equivalently think of this entire blue box, like we can think of this algorithm in the blue box as making O of T queries to these raw permutations and their inverses, instead of V star making queries to the oracle F. So this is what I mean by invoking the permutation view, is from now on, we'll think of V star as querying these permutations and their inverses instead of the graph oracle. And the key thing to note is that picking a uniformly random, picking X, Y1 through YR, and Z1 through ZR, uniformly random, it specifies a random instance in LES. So it specifies a random yes instance. And the min entropy over this distribution over, okay, so backing up a bit. And so now recall that we defined this yellow region, F sub W star, which is the set of all yes oracles that correspond to the maximizing witness W star. And now we can look at this pink region, which is the set of all raw permutations, which will lead to graph oracles in this yellow region in FW star. And now the key thing to note is that the uniform distribution over all raw permutations in this pink region, it's a high min entropy distribution. So in particular, the min entropy loss is quite low for this distribution. And so from the equivalence between graph oracles and permutations, to just say where we are now, we assumed the existence of a QCMA verifier V that distinguished yes instances from no instances. And then we hardwired the witness W star and defined V star, which is going to accept yes instances from F sub W star with high probability. And then we invoked this raw permutation view, and we thought of V star as querying a tuple of raw permutations instead of querying graph oracles. And from the equivalence between these two views, we can conclude that the probability over P sampled from PW star, that V star P outputs 1, is also at least 9/10. And now, since the min entropy of this distribution P sub W star is high, we can essentially decompose this uniform distribution over permutations in P sub W star into a convex combination of random permutation tuples satisfying the following. So number one, these random permutation tuples, they have a small number of fixed coordinates, and outside of the fixed coordinates, these permutations and their inverses are delta dense. So, and this is not too hard to prove. This is known from prior work. So we have this high min entropy distribution PW star, and we can essentially say that it's epsilon close to a convex combination of these random permutation tuples that are fixed on some coordinates, on a small number of coordinates, and outside of those fixed coordinates, they're delta dense. So just writing that mathematically, we can say that expectation over K, that the probability that V star to the GK outputs 1, it's also more or less, it's close to 9/10. In particular, this implies that there exists a permutation distribution G, meaning there exists some K in this convex combination that has a small number of fixed coordinates and is delta dense everywhere else, such that probability that V star, when it queries G, that it outputs 1, it's at least 9/10 minus epsilon. And now I'm in a position to invoke the quantum pseudorandomness conjecture. Now I'm going to just replace this delta dense with uniform. So the quantum pseudorandomness conjecture would imply that V star cannot distinguish between G, that is between G and a uniformly random permutation tuple that is conditioned on the same fixed coordinates. And this is because I can replace delta dense with uniform, assuming this quantum pseudorandomness conjecture. So now the final statement that we have is that the probability that V star to the P outputs 1, it's at least 9/10 minus some loss. And P is a permutation tuple that's fixed on some coordinates and is uniform everywhere else. So now translating raw permutations back to graph oracles. So if we have a uniformly random permutation tuple that is fixed on some coordinates, then this corresponds to a uniformly random yes graph oracle that's conditioned on some fixed structures. So translating back from permutations to graphs, fixed coordinates in the raw permutations, they invoke a yes graph oracles that have some that are conditioned on some fixed structures, which originate from these fixed coordinates in the permutation. So in particular, you can think of the pink region as permutations with fixed coordinates, and they invoke yes instances with some fixed structures. And so equivalently, again, from the equivalence between querying raw permutations and querying graph oracle, we now have a quantum algorithm V star that makes T queries and can distinguish between a uniformly random yes graph oracle with a fixed structure of small size and every no graph oracle. And now we're basically done. So now the last step is to show that if we have the existence of such a quantum algorithm V star, then this implies that there is a quantum algorithm W that makes poly T log big N queries, and it distinguishes between a uniformly random yes instance, so without any fixed structures, and a uniformly random no instance. So, and the way we do that is the main idea to do that is given a uniformly random yes or no graph oracle, we showed that there's a BQP reduction that uses random walks and plants these fixed components into the given oracle, and then it gives it to this quantum algorithm V star, and then invokes V star and outputs whatever V star outputs. So the main idea is to use V star to be able to distinguish between a uniformly random yes or no graph oracle. And the way we do that is by planting the fixed components and using random walks into the given uniformly random yes or no instance, and then feed that have V star query this oracle. And now this reduction, this implies that there is a quantum algorithm W that can distinguish that's making few queries and can distinguish between a uniformly random yes instance and a uniformly random no instance. So the yes instance has no restrictions and it doesn't have any fixed structures because of this reduction that plants these fixed structures. And but there's no lower bound for this distinguishing problem. And so we've achieved a contradiction. So this implies that there shouldn't have been a QCMA verifier V that was deciding the components problem in the first place, because if there were such a verifier V, then we could, through a series of reductions and invoking the quantum pseudorandomness conjecture, we can show the existence of this quantum algorithm W that can distinguish between uniformly random yes instances and no instances without any witness. And that's a contradiction. Yeah, and that's the result. Thank you.